Okay, I'm going to film now a short lesson on how to take the derivative of an inverse. Of course, there's the dog already. You close the door. This is a lesson that you might remember, or you may have blocked out of your memory from AB because you hated it when we did it and you never quite understood it. So let me tell you, understanding it is great. Knowing how to do it is what you need to do. It's honestly okay if you just know how to do the procedure. Hopefully the reason why resonates a little bit, because that'll make the procedure easier for you if you understand the why. But we already know how to take derivatives of inverse trig. We have formulas for those. I'm not going through the proofs of them. We did it last year. Hopefully you saw it last year or whatever, but there were proofs for them. But they also in Calc expect you to be able to take the derivative of a regular inverse, not using inverse trig, but the derivative of an inverse. So first I just wanted to give a little explanation or reminder on what inverses are. So if you remember, the definition of an inverse is that, the notation for an inverse is if f of x is the original function, f to the negative 1 of x is its inverse. Inverses are, they undo each other. So if I have x to the third as a function, the cube root of x is its inverse. And that's because the cube root of x to the third equals x. They undo each other like that. If you went and looked at the definition, it would say f of f to the negative first of x equals x. That's the definition of an inverse. That a function and inverse undo each other and leave you with x in the end. One of the other ways to define an inverse is they are reflections of each other graphically around the line y equals x. So if I have the function y equals x to the third, looks something like this, and the cube root of x, if I can draw this function looks like that. Well, these two things are reflections of each other over the line y equals x. So here's the line y equals x, and if I could reflect one over that line, I would get the other one. The other way to define an inverse, or to think about an inverse, is the domain of f is the range of the inverse of f. The range of f is the domain of the inverse of f. So in other words, all the order pairs are flipped. If I think about this function has the point 2,8, this function would have the point 8,2. So the cubic function would have the point 2,8, the inverse would have the function 8,2. So that's like your quick recap on what inverses are. The reason why that's important is because of this whole thing. Understanding that if I have the point 2,8 in an original function, its inverse would have the point 8,2. So while 2 would be an x value here, it would be a y value over here. And while 8 is a y value here, it's an x value here. So those things are flipped. Okay. The other thing that's true about inverses is that their derivatives are reciprocals of each other. Just reciprocals. So the derivative of one, if I flip it, I get the derivative of the other. Okay, that's a whole lot of information. The easiest way to go through it is to show you what a problem would look like, and then that kind of explains how this all ties together. So a problem might say, if I have a function where f of x is x to the third, find the derivative of the inverse at 8. That's what this is asking. So here is what you're going to do. Because the derivatives of functions and their inverses are reciprocals of each other, we need to find the derivative of the original and take its reciprocal with one catch. So let me say that again. Because functions and inverses have derivatives that are reciprocals of each other, we have to find the derivative of the original and flip it with one catch. Sorry, my dog's barking. I want to kill somebody. Not actually, just he's driving me nuts. Just fast forward the video for a second because I'm putting him outside. So rude. But I hate stopping a video and restarting, because then like I just feel like you won't come back to it. Okay, so here we go. The first thing I'm going to do when I'm given a function and asked to find the derivative of its inverse is the first thing I'm going to do is take the derivative of the function. So that my function's x to the third, 3x squared. The next thing I'm going to do is not flip it. I'm going to plug in, but be careful. Where they're asking me to find the derivative of the inverse at 8. This is an x value in the inverse function. That's like saying up here, my x value is 8. Well, because I'm going to base the derivative off of the original function, I can't think about 8 being an x value in the original function. I can't plug in 8. 8 is an x value in the inverse. So therefore, it was a y value in the original. And the x that goes with it is 2. That's what needs to get plugged in, because I'm using the original function to find the derivative. I'm using the original function's derivative to find the derivative of the inverse. So I am not going to plug in 8. I'm going to plug in 2. I'm going to plug in the, oh my God, that dog. I'm going to plug in the value that goes with this, analyzing it as if this is the x value of the inverse. So it is the y value of the original. So if I didn't have the points right up here, I would be taking the original, setting the original equal to 8, and solving and getting 2 as what I want to plug in. So I'm going to plug in x equals 2. I get the answer of 12. Now I take that 12 and I take the reciprocal of it. My answer is 1/12. Okay, so the method is easy. The why is really kind of complicated. So let's do a couple. Here's a function. Find the inverse of the derivative at 4. Step 1, take the derivative of f. Step 2, plug in, but don't plug in 4. I have to figure out what to plug in. Well, this 4 is an x value in the inverse, so it's a y value in the original. I have to set this equal to 4, or I'm replacing the y value with 4, and solve. So if I solve this, I do get x squared equals, add 12, I have 16. Divide by 8, I have 2. I have x is the positive or negative square root of 2. So this is what I need to plug in. So I'm going to plug in x equals the square root of 2. Well, why am I not plugging in the negative square root of 2? One thing I didn't mention back when I was just talking about what inverses are is that the inverses that we deal with have to be functions, so they have to pass the vertical line test. So sometimes we have to restrict the domain of things to make sure, like for example, if I had a parabola, its inverse is the square root curve. Well, it's not the entire thing, because then this wouldn't be a function. So we actually restrict the domain and range of the function itself. We just take the positive part so that its inverse is only the top half, not both top and bottom. All of that to say, for now, unless I have to tell you otherwise, if you end up with 2 solutions, a plus minus situation, take the positive one. All right, it's a small little topic, so I don't think they're going to go so in depth as to make you figure out which solution you need to use. So we're going to use that positive solution if we have a plus minus situation. So I'm going to plug in, I get 16 root 2. And my third step is flip. 1 over 16 root 2. That's my answer. Yes, you can leave the root 2 in the bottom. We don't have to rationalize. It's fine. All right. If f of x equals sine of x, what's the derivative of the inverse of root 2 over 2? Step 1, find the derivative of sine. I should just be a little more clear. Step 2, plug in. But do not plug in root 2 over 2. First of all, it wouldn't make sense. Take root 2 over 2 and set your original equal to that number and solve for x. Where's the sine equal to root 2 over 2? Think about the circle. right here, pi over 4. Yes, I know there are other places where the sine would equal root 2 over 2. Because sine goes like this, its inverse would go like this and be, its inverse would not pass the vertical line test. So we restrict the domain of sine as well. For now, and unless, we really have to get gnarly, but I don't think we do, we're going to be able to stay in the first quadrant and pick our solution there. So we got pi over 4. So second step, plug in. We get root 2 over 2. Third step, flip. 1 over root 2 over 2. Or we don't want to leave a fraction within a fraction, that's gross, so 2 over root 2. Now, I really don't want to blow your mind, but this was a trig problem, right? Well, shouldn't I have been able to do this with the trig derivatives, with inverse trig derivatives? Shouldn't I have been able to say, oh wait, well, I do know what the inverse of sine is. I know what the derivative of the inverse of sine is. Isn't the derivative 1 over the square root of 1 minus x squared? Is it minus? Oh my gosh, let me grab my calc book, is it for sure? Inverse sine. Yeah. So shouldn't I be able to get it this way? So shouldn't I be able to say 1 over the square root of 1 minus root 2 over 2 squared? Should these be the same? Well, I could just do algebra, or I could just get my calculator and just see. So on my calculator, oops, what did I do? Let's see what this is. 1 divided by square root of 1 minus root 2 over 2 squared is going to be 2 over 4, so 1/2. That's that. And 2 divided by root 2. Samesies. OMG. Don't you love when things work out? So because I picked a trig function, and I know what the derivative of the inverse of sine is, we know the formula for it. I could have just done it that way. Or I could have done, if we were in the groove of doing it the other way, I could have done it the other way. All right, then the final problem, tables. So the calculus or the AP people love to give tables and charts. So we just have to apply what we are thinking to this. It makes it a little trickier because this is like a procedure. Step 1, step 2, step 3. This is the same. It's actually easier, but you really need to understand what the procedure is. So if y is f of x, find the derivative of the inverse of y at 3. So you have to ask yourself, this is an x value in the inverse. So it is a y value in the original. I need to go to the table and see where 3 is a y value for the original. What's the x value that goes with it? 2. So what was the derivative of f at 2? -5. Flip that. That's my answer. All right, the great thing about a video is you can go back and watch that again, but I will say it again. This is an x value for the inverse, so it is a y value for the original. Go to the table. Where is f of x equal to 3? It's here. The x value is 2, which I don't really care what the x value is. I care about what the derivative is at that spot. Take my derivative and flip it. Because I'm still using the derivative of f to get the derivative of my inverse. Okay, that's super crazy. I know. I hope that some of that came back to you. I'm going to go do the work for the textbook problems, and then you're going to do the Khan Academy. This is split into 2 parts because the book problems are the more straightforward problems like these. The Khan Academy does the tables. So I couldn't find them both in one spot. So we're going to 2 different places. Yay! All right, thanks for watching. Tune in next time for Math That Blows Your Mind.